Okay, thank you and good morning. So, as Sue just said, I'm talking about the traffic engineering we introduced to our backbone that's based on IGP tuning. And it's talking about the experience that we made while doing this. And I just try to focus on those design issues that might be interesting to people that plan to do similar stuff. So this is an overview of the presentation. First, I'm trying to explain why we choose to do this approach, why we choose to do IGP tuning in our MPLS network. And then two main topics. First, how we get the traffic metrics. I quickly explain or try to give an overview of the LDP-based approach that we are using. And then also some issue that we saw with some data still missing in this and how we work with that. Next main topic is simulation and optimization. I'm going to talk about what is important when defining the topology to use traffic engineering on, some metric design issues we ran into across, and then I'm going to talk about what we use as a virtual topology and how that looks like. Then finally, a summarization of our conclusions and what we intend to do in the future. So, in order to understand the motivation for our approach, let me first give you a few words on the network design that we are actually using in our network. That is, we actually do use MPLS and LDP for all traffic. That is for VPN as well as for public IP traffic. And so our backbone mainly has two types of MPLS routers, which we call label switch routers or LSR and label edge routers or LER. Commonly they're probably named P and PE, but I like the word label switch router because it makes some of their properties more clear. The label switch routers only do label switching, no IP lookups, so they don't have to have the full routing table. We actually have a BGP-free core. The label edge routers, of course, do have to have the full routing table. They have to do the IP lookup to decide what egress LER to send the traffic towards and push the appropriate label. However, the network is not all that clear. There are some routers which are of a mixed type. They have LSR functionality as well as LER. And we'll see that there are some issues about this. So the main line, we use MPLS for forwarding in the core, but the routing is still determined by the IGP. Well, short visual to explain this. The red links only carry MPLS traffic. The green links IP traffic as to the customers. So the MPLS cloud can be thought of as consisting as of the MPLS core with the switching routers and the edge with the edge routers. Why did we actually decide for IGP metric tuning? One statement you can usually hear when talking about traffic engineering is that, well, if you have an MPLS network, you can easily do traffic engineering by RSVP-based explicit routing. Before deciding, we actually did some research. We first tried to get our traffic metrics. Then we tried different designs, different algorithms, tools from different vendors on our particular topology and on our traffic metrics, and had a closer look on what possible results would be. So the result was that, of course, optimization of explicit routing was somewhat better when compared to metric tuning, but the difference was not that big. It was a relatively small difference. And on the other hand, explicit routing promised to introduce a lot of new risks and pitfalls, the complexity thing. And on the other hand, SPF-based routing is well understood by operations. It's running. And so in this trade-off between complexity and optimization, we just decided that the IGP approach would be good enough. Well, this is a result of a short study done by Carradine based on our data. They tried to visualize the result for different approaches. In this diagram, we have the maximum link utilization in the normal case on the x-axis, on the y-axis, the worst failure link utilization. So this is the theoretical optimum. When just using default metrics with no tuning, we would be there. And these are different results for different approaches of traffic engineering. Actually, I can't comment much on those with dynamic explicit routing, but these numbers were such that we actually could verify them exactly. Actually, before introducing traffic engineering, we haven't been there. We had some kind of manual metric tuning, and so before we started traffic engineering, we were about here. So from here to there, there's some way. From there to there, it's not that much. So we decided for this point. Okay, it's always critical for traffic engineering to actually know the traffic metrics, demands from end to end, and our approach is what we call the LDP-based approach. It has been explained in more detail in a previous presentation, and if you are interested in some of the details, I'd suggest to ask Stefan Schnitter directly. He actually developed and implemented the exact algorithm. So I want just to give an overview of the prerequisites that are necessary for this approach. First thing is we have to poll the MPLS counters from all the label switch routers and some of the actual routing information. Then we have to know the topology, as it can be derived from router configurations, and this allows us to get the real traffic metrics for all forwarding equivalence classes between all the LSRs. So with this approach, we actually can measure the exact traffic metrics without having to do the full mesh of TE tunnels, without having to mess with actual routing. This is how the commands we use for polling look like on Juniper routers. It's show LDP traffic statistics and some kind of show route table. We do have the FEC, bytes switched in this FEC, and what interface those bytes go to. And that is basically what we need. One interesting thing about the Junipers is that they distinguish between transit and ingress LDP traffic. Transit meaning traffic that is purely MPLS switched, while ingress meaning packets that come into the router as IP packets and then get an MPLS label. On Cisco routers, it's just a show MPLS forwarding table. And again, this gives us all we need: the FEC, the bytes switched in this FEC, and the outgoing interface. This also nicely shows what happens with ECMP multipath and shows all the outgoing interfaces and the exact distribution. However, we ran into some issue with what Cisco understands under bytes text switched in this context. And it turned out that this really only counts and reports the MPLS packets. So what Juniper says calls transit. And so far we have no feasible way of counting the IP packets per FEC and read them in a feasible manner, at least as of now. So the problem for our approach is when these are missing, that we wrongly see the directly connected IP sources at the next MPLS hop and not at the router where the traffic is actually sourced. This only affects those routers of the mixed LSR LE type, and fortunately there are only a few routers of this type in our network. However, they do create a lot of traffic, so it's still important to cope with this situation. The good thing is that we at least know how much traffic is missing from the interface counters. try to visualize. Again, we have the MPLS design, and let's say we are looking at traffic that goes from this LER on that path to that LER. So because, let's say this is a Cisco router, then it does not count the packets coming into on the IP link. And so actually for our approach, it looks like the traffic was sourced here. We know that it's wrong, or that some traffic is missing, because interface counters on this link really report more traffic than we actually see by LDP counters. But we still don't know whether a traffic seen on this link goes over there, or maybe over there, or wherever. So in order to work with this situation, we developed two algorithms for extrapolating this missing data. One is based on data from real LERs that might be connected to the node. And if that's not available, we have another algorithm that just uses the traffic coming back from all possible destinations and use this to extrapolate the distribution of the missing traffic. And we can use whichever of those two methods that fits best for each affected router. Okay, next topic is the topology. At least in large networks with hundreds of routers in the backbone and even more routers in the edge, you probably have to select a subtopology for doing traffic engineering on. One of the reasons being that there might be scalability issues with the tools for simulation and optimization. Our impression was that this runs fine if you have less than 100 routers and maybe a few thousand demands in the TE core, but that probably problems would occur when there were hundreds of routers and tens of thousands of demands to be simulated and optimized. Of course, it depends on the exact tool you're using, on the exact algorithm and everything. But then also the edge and regional routers might not really contribute much to the actual purpose of traffic engineering. So it's not really necessary to include all the routers. But it is necessary to include all the long and expensive links, because that's where the money can be saved. Probably the international or intercontinental links are important. And of course, all the routers that terminate these links distribute traffic on them. And we also need some kind of representation for the routers that are outside of the TE topology. So things would be easy in that kind of ideal topology where we had a traffic engineering core and regions just connected by one link to the TE core. However, in reality, it's more complicated. Regions are likely to have more than one uplink to the core. Maybe they have even links between them. So it becomes more complicated to select the right subtopology, and it might easily become a trade-off between exactness and simplicity for the simulations on the other hand. Then we also ran into some issues concerning the IGP metric design. For traffic engineering, it's a requirement, or at least good idea, to be as liberal as possible with the metrics that the optimization algorithm is allowed to select. So the optimization algorithm can choose as low or some high metrics as it considers useful. And then on the other hand, use large metrics in the regions so that they don't mess with the core metrics, so we get a predictable routing and the traffic metrics stay stable. On the other hand, if you're using IBGP route reflection, there are some requirements mentioned in RFC 3345 concerning the link metrics, and it says that intercluster links must always have a higher IGP metric than any link within a cluster. And this is required to be sure to avoid persistent route oscillation. Well, this is easily in contradiction, because intercluster links frequently are or are likely to be within a regional network, while the intra-cluster links are likely to be within a region, while the inter-cluster links are likely to be in the TE topology. So, well, on the first glance, you might think, well, if you're using ISIS, then the level 1, level 2 boundary may help, because the level 2 actually doesn't have to deal with all the details from the level 1 areas. In fact, it does help in some cases, but not in all, since route leaking still causes interference. And route linking, on the other hand, is required if you're running on the BGP-free core. So what we did is some IGP metric design like this. This is an example of a typical POP. The two LSRs are in the TE topology, and all their linked metrics are in ISIS level 2, and these are actually set by the optimization tool. And in order to be sure that the level 1 links don't mess with the TE topology, we set some very high metrics where possible and where required, but asymmetrically still use the old small metrics on the side that is sawn from the network to the LER, so that the BGP still gets what it's used to see, and we don't mess with the BGP decision process. Okay, well, last topic, virtual topology. In the tools, we do use simulations for the normal case, just simulating the IGP, as well as simulating the IGP for all possible failure scenarios. In order for this to work, we do have to represent the edge and regional routers in some suitable way. That should be exact for the normal case and at least roughly represent the traffic for failure cases. Since our network in most cases has a very regular POP design with two LSRs and a lot of edge routers and several regional POPs connected to it, we were able to have a quite regular design for virtual routers, and this is for each POP, we have one virtual router that is symmetrically connected to both LSRs and two that are asymmetrically connected. So this looks like this. On the left hand, you see an example of the real topology. Of course, there are more edge routers, more regions connected to each core POP, but I think this gives you an idea. And on the right side, you see how this is represented in our virtual topology. One symmetrically connected router and two asymmetrically connected routers. And the IGP metrics are always set to the smallest value occurring in the real network, which happens to be on the links with the highest bandwidth. So we at least have the biggest demands simulated correctly, even in case of any failure. Okay, then let me summarize. MPLS can actually help traffic engineering, even if it's IGP-based traffic engineering, no RSVP. And this is by the per FEC counters that MPLS can provide. It's important to select the subtopology for traffic engineering carefully, and you may have trade-offs between exactness and feasibility and simplicity. You have to be careful with the IGP metric design, at least if you're using iBGP route reflection. And then the result is, at least in our network, you can have fairly good optimization, maybe not perfect, but fairly good, without having to spend much CapEx or OpEx. And it's important that we can do simulation even on any failure case, so we can verify that SLAs are not compromised even when increasing the efficiency of the backbone. What we are going to do in the future is still try to improve the simulation and optimization accuracy where possible at a reasonable cost. First thing that we are looking at right now is getting the per FEC counters even for IP packets, even for Cisco routers, and we're in discussion with Cisco, and they're still trying to decide of where and when and how to put in some useful function. Then an ongoing thing is to optimize the virtual topology, fine-tune the trade-offs. And one thing we might do in the future is include the big redundant peerings in the simulation. What we also would like to do in the future, maybe more in the far future, is class-based traffic engineering, so having different routing for certain QoS classes. And from my point of view, it's important that we get a solution that really has the forwarding decision not only based on IP address or MPLS label, but also on the precedence or experimental bits. And the approach can be anything like multi-topology ISIs or like a mixed scenario, still IGP routing for best effort and explicit routing for some special QoS class. Okay, that's what I wanted to say. Are there questions?
I'm going to ask a couple questions of Martin. Is this on? Yeah, okay, good. I can't tell right here. Susan also asked me to give a couple addresses that might be infected with worms or have problems. If you have concerns about, if you're that address and you have concerns, go back and see the back table or, you know, wander back. John.Sato at dli.net, MIZ as in ZUNO at net1.co.jp. You might want to check and see what's going on. If you have questions, go back to the back guys. They'll give you the details. First, what tools did you use for collection of your statistics and all that cool stuff? Did you screen scrape? Did you MIB-walk? Did you pull some other cool tools? How did you collect all the data and keep it accurate, and how do you keep it going in a daily basis?
So all the tools for collecting the data, for creating the topology and traffic metrics are sort of self-made, a lot of Perl scripts, and we are actually using just the CLI telnet to the routers to regularly pull the counters.
Are you willing to share these, or is this something that's sort of specific to your network?
Well, this, of course, has a lot of edges that are quite specific to our network. However, if they're interested, we might create the contact to, perhaps to Stefan from T-Systems. Maybe they are interested in helping. Okay.
Why were you considering MT-ISIS or some of the other things? Your last slide says multi-topology, ISIS and IGP mixed scenarios. Could you give us a little bit more details on why you were thinking of that for forwarding decisions, precedent bits, or did you sort of mix them two together?
Okay. Well, one thing is that we are happy with the IGP metric tuning based approach, and we are quite reluctant to introduce a full mesh of tunnels for the whole traffic, including all the best effort traffic. So we won't use, we are really looking forward to an approach that allows us to still do simple IGP tuning, at least for the mass of the traffic for the best effort class. So this is one point. And the other thing is, well, we want to do traffic engineering on the TE core, not on some edge-to-edge based approach. So the router actually at the border of the TE topology has to do the decision of what routing to use for each packet. So we do have to have this forwarding based on the QoS bits.
Good. And last question is probably always what everyone wants to know, which is, what was your worst difficulty in getting all of this put together?
Well, technically, maybe the most interesting thing was to actually get the calculation of the traffic metrics running. And organizational, there's of course a lot of problems in companies as big as ours to get planning, operations, development, research, and engineering all together.
Thank you again, Martin. We really appreciate the time, and I'll take the next speaker, as I think we're out of time. Excuse me, I don't want to be the only questions. You can
Yes.
just
Yes.
sit and wait. Go ahead.
Yeah, Sergio, France Telecom. So, very good presentation. I wanted to tell you that. I have two questions. One is, do you consider the case where you have ISIS with traffic engineering extensions and the ISIST? And the other question is, you were talking about the SLA kind of motivations. Do you have in mind, because there are some kind of TV or voice and video carry out of those tunnels?
I'm not sure whether I got that right. The first question was on TE extensions of ISIS.
Yes.
I know there is a separate link metric available for the TE case, as it is used by the dynamic RSVP-based approaches.
Yes.
So there's no point in using this if we just have one IGP for our routing. We just have this one topology. I know different link metrics are there, but so far we don't have any possibility to use these. The other question was concerning SLAs. Well, we do have certain SLAs like latency from end to end, depending on the region, and by using a simulation, we make sure that these are still met.
Thank you.